Okay, so resistors in series are when you have multiple resistors that lie along a single path in a circuit. So this is when there are multiple resistors that lie along a single path in a circuit. It's like one right after the other, so it's a series. So in terms of what this could look like, if you were to think about the actual diagram of this, if here's like my power supply, it'd be like having one light bulb, and then another light bulb, and then another light bulb, and then back to the other end of my power supply. If I were to think about this in terms of a circuit diagram, here's my power supply, here's my first resistor, my second resistor, my third resistor. You could even draw it like this. It doesn't really matter. There's my one resistor, my second resistor, my third resistor. Okay. These are all diagramming out resistors in series. So if we kind of think about how this is connected, in terms of what is true, is that the current that comes out of the power supply must go through every single resistor. Must go through every resistor. There's nowhere else for it to go. So if my current is coming out, like it has to go through that resistor, it has to go through that resistor, it has to go through that resistor, it has to come back to the power supply. So there are no other paths for the current to go through. So in terms of what that means in an equation, it means that my total current that's coming out of my power supply has to equal the current that's going through my first resistor, has to equal the current that's going through my second resistor, has to equal the current that's going through the third resistor, and so on. Okay. Now, in terms of voltages, if I think about my voltages, remember I've got my little electron guys here, and I'm actually going to make this a little bit bigger to see. So let's say I've got my 3 resistors, and oops. Oh, this is a magnetic. I can't do it on this. Golly. Okay, I have to bring. I gotta bring this board in. Rewind. Let me draw this a little bit bigger. So this is like resistor 1, resistor 2, resistor 3, and let's just say this is 12 volts. So what that means is, remember that every resistor that is coming out of my power supply, like they're super excited, they all have 12 volts, and when they go through this first resistor, they're like, I'm gonna bring this over here. They're like, oh, I've lost some energy. And I'm gonna, just for the sake of, I don't have all my magnets here, when they go through this resistor, they're like, oh dear. And then when they get to this final resistor, remember, when they get through this final resistor, there's no other resistors to go to. They have to have a low voltage. On this end, they have to have 0 volts. And so here they're just like sad, they've got no energy, they don't know what to do. So if we think about from here to here, I have to lose 12 volts. Now, in order for that to happen, I've got to lose some energy through each of these resistors. If they're the exact same light bulb, then it makes sense that they would split them up evenly. So I've got 3 identical light bulbs. I have 12 volts total, so it makes sense that they're each going to get, there's going to be 4 volts here, 4 volts here, and 4 volts here. So it means if I start with 12 volts and I lose 4, I'm going to have 8 when I get through that resistor. And then he's going to have 8. And so then he's going to lose 4 volts here, so he's going to only have 4 left. And he's going to come through here, and he's going to lose his last 4 and come back to the other side of the power supply with a low voltage of 0. So we can see in terms of the voltage relationship, because the electron has to lose all of its energy by the time it returns to the power supply, there's a relationship for voltage. So the voltage for resistors in series must be split up. Amongst the resistors. So my total voltage is going to equal the voltage I lose in resistor 1, the voltage plus the voltage I lose in resistor 2, plus the voltage I lose in resistor 3, etc. Okay? So these are 2 key equations for resistors in series. Like, I'm going to take these and run with them. Okay? So I'm going to come back here to this. I can put up this board. So if those are my 2 equations, I'm going to derive a relationship. And you do not have to copy this down. I just want you to see where I'm going with this. So we know that my total voltage is the sum of my individual voltages. But remember Ohm's law. Ohm's law says that I is equal to V over R. And I can actually rearrange this to make it say that V is equal to I times R. And as long as my subscripts agree, I can use this throughout this entire thing. Like, I could say V total is I total times R total. And I could say V1 is I1, R1, V2 equals I2, R2, etc. So if that's true, if Ohm's law is true, I could rewrite this equation. And instead of writing V total, I could say this is I total, R total. And instead of saying V1, I could say this is I1, R1. Instead of V2, I could say this is I2, R2. Instead of V3, I could say I3, R3, etc. Okay? So it's just a different way of looking at the voltage relationship. But remember that for resistors in series, the currents are all the same. So if the currents are all the same, that means every single one of those I values is the same. And I could actually cross those out, and we end up getting this relationship for resistors in series. R total is equal to R1 plus R2 plus R3 plus blah, 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 meaning that the equivalent resistance for resistors in series is equal to the sum of the individual resistors. And so this is what I want you to write down. This is important. That for resistors in series, the total resistance or the equivalent resistance of those resistors in series is just equal to the sum of the individual resistors. And so now we'll go through just some examples of how do you apply this mathematically.